Hey, thanks everyone for taking the time to listen to our presentation. Myself, along with Megan Van Veen, Ryan Kromer, and Richard Carter, will be presenting some work we've gone on to do after our years as graduate students as part of the Rghrp group at Queen's. Just a quick refresher of how a number of current BGC team members kind of fit into the overall Rghrp timeline at Queen's. The initial exploratory work into potential study sites, data collection techniques, was done by Dave Gauthier and Matt Lotto, and this would go on to form the basis for a lot of future work. Following this, several groups of students, including myself, Megan, Ryan, and Richard, along with Matthew Anderson, Emily Rowe, and Angus McPhail, would go on to help refine these data collection techniques, improve change detection processing workflow, use this data to develop novel analyses that would help support, in general, hazard and risk assessment along rock slopes along linear infrastructure, specifically railways. So I'm just going to show sort of a rapid fire snapshot of each of our work, and then we'll jump into how some of this work is continuing to be applied as part of BGC projects. So most of you should be familiar with this. Here's what some of the data we're often working with looked like. 3D change maps showing talus movements and rockfall events above a section of track above a railway in the White Canyon. So using these data, Megan worked on techniques to extract rockfall events in a semi-automatic way from sequential terrestrial LiDAR scans in order to build detailed rockfall frequency magnitude relationships, in this case, once again, in the White Canyon. Ryan developed automated workflows for data collection and processing techniques, allowing for the detection of small precursor pre-failure slope deformations leading up to rockfall events. His work helped advance our understanding of precursor rockfall events and the ability to forecast time to failure. Also, as part of this work, he and Emily explored the influence of rock mass structure on the ability to detect precursor deformations, providing insight into where these techniques may be useful for future monitoring. Myself and Matthew Anderson focus on the development of new rockfall modeling techniques, which could leverage the high-resolution datasets being collected at the Rghrp study sites using terrestrial laser scanning and photogrammetry data collection. We use the ever-growing database of detected rockfall events to test these new techniques and show their actual potential as practical tools. Richard explored really what could be done and extracted from a single aerial LiDAR dataset at the regional scale here instead of at the slope-specific scale, developing semi-automatic terrain classification and hazard assessment methods, which could be applied over large areas for rock slopes. And this brings us to now. The techniques developed as part of the Rghrp program have since been applied and are in use currently at numerous BGC project sites. They help us help our clients with their complex geoscience problems. This includes several transportation projects and also includes other sectors we work in, such as pipelines, mining, energy development, and communities. So now I'll hand it off to Megan, Richard, and Ryan to talk about how we're using some of this work on our projects.
Thank you, Zach. This is Richard speaking. I'm going to talk about some work that was carried out about a year ago for CN, where we were asked to help them develop an understanding of hazard density for a particular stretch of track on the Yale subdivision. So basically, the objective of the project was to figure out where they're likely coming from and figuring out where they're going as well. So there was a hazard identification component and a modeling component. The study area, as mentioned, was a stretch of track in the Yale subdivision, characterized by large natural slopes, which are thickly vegetated. Because of this, if you're staring at a fallen block on the track, it's not always apparent where it's coming from. So that was kind of the impetus for this study, was to develop a better understanding of hazard potential in different areas. The scope of work was really focused on hazard density and providing this type of output, but it led to some interesting research and a new technique. So I'm going to present the project work we did and then talk about some of the research spin-offs that came out of it. So like so many of these other regional scale studies, our starting point was an airborne LiDAR survey and some orthoimagery. We carried out some cursory analysis on that and did some literature review to identify our potential rockfall sources, which is what you're seeing in black on the top of your screen. And then in order to understand hazard density and quantify the likelihood of a rockfall hazard reaching a given point, we needed to come up with some sort of metric to use for frequency. And we didn't have the time or really the budget to really dig into rockfall frequency for all of the source zones that we identified. So as a proxy, we came up with this concept of regional rockfall potential, which is what you're seeing on the bottom of your screen, where the color represents the proportional rockfall potential of an identified source. So basically, this means a larger source zone will be given a larger proportion of the regional rockfall potential. Once we had all the sources mapped, now we can do some modeling. So on the top of your screen, you're seeing the output of a single model run. The pink colors represent a high runout probability for a given point, where blue represents a relatively lower probability. And the model we used was called FlowR. It's an empirical model that basically finds any credible path that an object might take to propagate down slope. So we ran this model once per source zone, and on the bottom of your screen, you're seeing the cumulative result of this. So each model was combined and took this proportional regional rockfall potential into account. And what you see is kind of this heat map that gives you a sense of regional rockfall hazard traffic. And this is kind of a standard modeling output. It takes a large area into account and tells you where there's high traffic and where your lower runout probability areas are. So it kind of answers the question of where rockfalls are likely to go. But after doing the work, we kind of realized that inherently in the way we set up this process, we're able to also answer the inverse of that question, which is where did they come from? So now you can see on your screen, there's a hypothetical rock from heaven, a fallen block on the track that you don't know the origin of. And then all of the thin black outlines, which might be a little bit hard to see, are the extents of all of the runout polygons created through the modeling exercise. So with this information, you're able to figure out all of the source zones that could have impacted that particular point through a simple GIS query. So take the point, take the runout polygons, and that lets you figure out which source zones may have impacted that point. And then because we have this proportional regional rockfall potential, which is basically our frequency measurement, and we also have the runout probability through the modeling exercise, we're able to take these two parameters and adjust the proportional rockfall potential to be relative to this specific point. So rather than the colors of the source zones now representing the regional rockfall potential, they're representing the adjusted rockfall potential specific to that point. So just to kind of drive home how this works, I've taken one example, which is this large source that was in the middle of the screen. It's responsible for about 15% of the regional rockfall potential in the hazard identification exercise. And then in the middle of the screen, you can see the single model output, where you can see that at the point of interest, there's a 0.005% chance of an object reaching this point from that source. Then with those two parameters, you're able to adjust and create this relative rockfall potential for that point, which is a 0.75% chance that a rock from that source reached this particular location. So you go from that 15% of regional rockfall potential to that 0.75% chance of relative potential. So this is kind of a simple extension of conventional rockfall modeling that adds a lot of value without a lot of extra effort, and kind of helps to answer that question that comes up in this meeting every year of where are these rocks from heaven coming from and how can we understand them better. And now I'm going to turn it over to Megan to talk about some of the regional scale work we've been doing at VGC.
Thanks, Richard. So one of the tools that we explored earlier in the Rghrp was the use of airborne LiDAR scanning data to perform change detection analysis similar to the process used for terrestrial LiDAR. However, this technique wasn't widely explored in a lot of our research. So today I'm going to provide some examples of how we've applied these techniques for regional slope movement screening applications. So earlier in the Rghrp, we used these techniques at a couple of sites to monitor longer term change. The example here shown is the 10-mile slide near Lillooet, and we were able to use historically collected data from 2006 compared with newer data collected in 2016. And we did the same for several of the sites along the Hope to Ashcroft corridor using data collected in 2014 and 2015. However, these repeat data sets were only available for a couple of the sites that we knew were specifically active. A few years later, and with some improved data processing methods, we applied these techniques to a 37-mile stretch of CN's river subdivision, and we delivered the results as a series of figures. But as much as the use of airborne LiDAR data is handy for quantifying change at these sites we're already interested in, the ability to collect data over vast areas also allows us to use it as a screening tool to identify sites that maybe we weren't highly prioritizing, with the catch that we do need to have 2 data sets available to do this. So BGC uses a software developed in-house called Cambio to help our clients manage geohazards and assets across a number of different industries, ranging from pipelines, railways, other forms of transportation, as well as hydro reservoirs and tailings dams. And this includes several hundreds of thousands of kilometers of linear infrastructure that we manage. Earlier this summer, we had a client reach out to us and they asked us to perform LiDAR change detection over 1,600 kilometers squared of pipeline right of way. So the client had flown their whole corridor with airborne LiDAR in 2019, and we were able to leverage some off-the-shelf publicly available data to use as a baseline. Because we were working with such a large area, we developed a streamlined set of tools to manage, process, and integrate all of this data into our online Geohazard platform, an example of which is shown here. We also developed a number of analytical tools to help experts and non-experts visualize and understand the data, such as interactive and editable color scales, point and polygon statistics, an example of which is shown on the left here. So the ability to query points or specific polygons and get information about the change that's occurred at those locations. And then we also developed this profile extraction tool where you can cut profiles through the different sets of airborne LiDAR data or topography data sets and measure the change at specific locations in different directions. And then we continued by applying these techniques to another couple hundred kilometers of pipeline right of way, as well as an 80-kilometer long hydro reservoir. So back when we started using this airborne LiDAR change detection technique, we really were limited only to a single site type of analysis, both because of the highly manual nature of the processing and also the availability of data. Eventually, we had developed the methods enough that we're able to apply this at sort of the subdivision scale with some automation, although the process of generating figures or drawings to display the results was still quite an onerous process. Today, we've built on these tools so that we can capitalize on the large amounts of airborne LiDAR data that are now being collected over areas, and we can apply them on a regional scale with a fairly automated process. And then we can integrate these results into an online environment where there's no limitations such as expensive computer software to access and understand the results at both a qualitative and a quantitative level. And then we can use this as a screening tool over large areas or for detailed analysis at specific sites. And because all this data lives in an online GIS type environment, we can easily integrate it with other information we have, such as site inspection notes, photographs, instrumentation, and other types of remote sensing data, such as INSAR. And now I'll pass it over to Ryan.
Thank you, Megan. We're going to zoom in now to the site scale and talk about automated monitoring and change detection using tools such as terrestrial LiDAR and terrestrial photogrammetry. One of the first applications of automated monitoring occurred along the CN Squamish line on mile 150.8. Tools were developed to automatically monitor the slope with real-time change detection for this site example, which is a rock slope failure which occurred on the 9th of February of 2015. This is an emergency response scenario where the goal of the monitoring was to identify any potential pre-failure deformation. The software was able to process scans within 5 to 10 minutes after data collection. The second example I'm going to show now is more long-term monitoring. This site is at Manitou Springs, Colorado, which is just southwest of Denver. This is a fixed photogrammetric system, so there's 5 camera stations monitoring the slope. Each one of the stations uploads photos to a server for data processing, where a 3D model is produced, and the 3D models are then used to compare change over time. There's 2 systems currently running in Colorado, one just west of Denver and Idaho Springs. That system's been running since March of 2018, and the current system is running since December of 2019. In general, for both LiDAR and photogrammetry, the following generalized workflow applies. So the first step is to collect data. This is usually done with a laptop or microcomputer. The microcomputer schedules data collection as well as uploads data to a server. For photogrammetry specifically, 3D model is constructed with structure from motion algorithms. For both LiDAR and photogrammetry, registration is needed. This is alignment of the clouds so that they're in the same reference frame so that change detection can be done. The second step in the processing workflow is filtering of outlier points and filtering of vegetation. So I've outlined in green identified vegetation points. This can be done manually or with automated classification techniques. And these vegetation points are then used to subtract out vegetation points in subsequent point clouds over time. And the last step is change detection, where a geometrical comparison between point clouds is done to detect rockfalls or pre-failure deformation. So I've highlighted in the yellow box an example of a rockfall in blue. I'm going to show the results from monitoring at the Manitou Springs site since the 24th of January of 2020 up until the 2nd of December of 2020. A total of 36 rockfalls were identified with volumes between 0.001 cubic meters and 1 cubic meters. Now I've identified here in the yellow box an interesting example where there's an area of pre-failure deformation as well as an area of rockfall detachment and then a deposition on the ledge. You can see this highlighted on the right, where you see a wedge-shaped block which is descended, and then the toe of this wedge-shaped block has actually deposited on this ledge. So this tool can be used to monitor rockfall activity, slope degradation, and it can also be used to detect pre-failure deformation before a rockfall event. This particular system has a detection limit of plus or minus 5 centimeters. Now, the last example I'm going to show is application of these techniques to a landslide case study. This case study is located in the Siguas Valley in southern Peru. And you can see on the bottom left, the landslide being monitored is encroaching onto a state highway. And just upslope of the landslide, you can see active farming. This area is heavily irrigated. So this landslide example is analogous to the Ashcroft slides in British Columbia. And you can see on the right, one of the monitoring stations, one of the 5 monitoring stations overlooking the landslide. I've highlighted in this yellow a section of rock wall that's actually detached and moved towards us. So this is quite an active landslide with measured movements of over a meter a year. And this particular case example also used targets, which could be detected automatically to help with aligning the scans and as well to help track movements over time. So in summary, automated monitoring can be used for long-term observation of landslides or rockfalls, but it can also be used specifically LiDAR for emergency response monitoring, where the work is underway under a particular hazard. And lower cost solutions are currently in development, including lower cost LiDAR units, as well as lower cost consumer grade cameras with, in this example, Raspberry Pi microcomputers.
So after those great presentations, the usefulness of remote sensing data sets for slope monitoring and risk management is really evident in many of the projects we work on. And this is an extension directly of the awesome work that was done and continues to be done as part of the RGHRP. Data collection methods and processing techniques are continuing to develop, making data more widely available at more sites and over larger areas. Ongoing research into how we can manage and extract meaningful information from this data is critical. Our time at the RGHRP provided us a strong background in remote sensing techniques, data management, and risk assessment, as well as strong communication skills, all of which set us up for success in consulting and also in further research endeavors, as everyone's sort of keen interest in all things cutting edge have led to ongoing research at BGC and is part of other university-funded research projects. Thanks very much for the opportunity to present to you guys again, and if you have any questions, let us know.